Honors Chemistry, and welcome to the back part of Chapter 14. This should be 14.7 through 14.9, I believe, where we're going to talk a little bit about weak acids and weak bases, and then basically we get into, well, we have to talk about water so that we can then talk about how to calculate pH. So, weak acids and weak bases, we've already alluded to this way back in first semester, but a strong electrolyte is something that what? Right, it's something that dissociates completely, right? So when I say that it dissociates completely, that means whatever it is that I put into the aqueous solution no longer exists. And the only thing that exists in solution are these separated ions of whatever that thing was, right? Something that is a weak electrolyte dissociates some. So that means in this particular instance, there is some of the original compound floating around in the aqueous solution, and there is some of the dissociated ions floating around in solution, right? So let's talk about some examples. So when I talk about a strong electrolyte like HCl, what that means is when I put that in water, that dissociates completely into H plus and Cl minus. That means that in solution, there is no HCl left, right? It is all this and all of that, right? Likewise, when I put NaOH in water, right? Strong electrolyte, which means that it is all now present as Na ions and OH ions, and there is no sodium hydroxide. It is all now sodium ions, hydroxide ions, right? Which then, by extension, let's say that I started off with 1 molar HCl, I now have 1 molar H plus and 1 molar Cl minus. Yes, does that make sense? Or if I had 1 molar sodium hydroxide, I now have 1 molar sodium and 1 molar hydroxide. Yes? All right, so then that brings us to the case of weak electrolytes, which are different. So if I have some C2H3O2, which is a weak electrolyte, this dissociates some, right? Which means that there is some of this and some of this and some of this. So if I were to say that I have a 1 molar solution of acetic acid, I actually, it is some complicated math to figure out what that means about the concentration of H plus, okay? So that being said, when we talk about calculating pH, we are going to stay in the land of strong electrolytes. Strong electrolytes, because they dissociate completely, are also strong acids and bases. Okay, so one more time. Things that are classified as strong electrolytes are also strong acids or strong bases. Okay, which means that strong bases, again, are the soluble metal hydroxides. Strong acids, there is a list of those back in chapter 5, I believe it is. So go back to that. But for all of those, right, that's where we're pretty much going to stay in terms of pH calculation, because like I said, the math from here to here is beyond where we are right now, okay? And so then, in the outline, I do believe I asked you to discuss a little bit about what that means for Bronsted-Lowry conjugate pairs, and your book does talk about it a little bit, and you just have to understand it to the extent that it's in your book, because for time purposes, we are just going to cut the discussion there. All right, so autoionization of water. Now, on its own, this particular section might seem kind of weird, and you're like, what? I don't know, what is it talking about? This, though, is the foundation of how we calculate pH for aqueous solutions. So I cannot stress enough that it's important, okay? So, first of all, this happens to some extent in water. As in water, auto, meaning on its own, forms ions, okay? Specifically, two waters can react, right, to form a hydronium and a hydroxide, right? And that happens to some extent all on its own, spontaneously, in any sample of liquid water, okay? Now, not a whole lot, right, but it does explain why even pure water has a very low level of conductivity, because even with nothing else in it, there are some ions formed from the spontaneous autoionization of water. So, then there have been enough tests done to know exactly how much water ionizes, right? water auto-ionizes, which gives us Kw, where Kw is a constant, right, that basically fixes, right, the ratio of hydronium to hydroxide in an aqueous solution, right? Kw is a constant that fixes the ratio of hydronium to hydroxide in an aqueous solution. It says that, and so this is molarity, right? So these square brackets, are molarities, right? So this is the molarity of my H3O plus, and this is the molarity of my hydroxide ion, right? So the molarity of those two multiplied is always going to be 1 times 10 to the negative 14th. Yes? All right. So what that means then is if I'm looking at an acidic solution, right, my H3O plus concentration is going to be greater than my hydroxide ion concentration. Yes? The product is still going to be 1 times 10 to the negative 14th, but hydronium is going to be bigger. A basic solution would require that my hydronium ion is going to be less than my hydroxide ion, right? And again, the product is still going to be 1 times 10 to the negative 14th. Finally, that brings us to, well, what does it mean to have a neutral solution? Well, you tell me. Right, that's going to be the situation where hydronium is equal to hydroxide, and looking back at this equation up here, what that means is it's equal to 1 times 10 to the negative 7th molar, yes, in a neutral solution. Does that make sense? All right. So then here's one of the figures from your book that just sort of tries to emphasize that, right? Where, so here, right, if my hydronium ion concentration is 0, or is 10 to the negative 0, this is going to be 10 to the negative 14th because the product always has to be 1 times 10 to the negative 14th, right? Or here, for example, if the concentration of hydronium is 10 to the negative 4, this one is going to be 10 to the negative 10 because, again, the product always has to be 1 times 10 to the negative 14th. Yes? All right. And again, acidic solutions, right, mean that my hydronium is greater than my hydroxide, right, and flipped when we get over here to the basic section. Yes? All right. Now, how to calculate pH. So pH is the negative log of my hydronium ion concentration molarity, and this is the negative log of my hydroxide ion concentration, okay? Now, these are log base 10s, right? So really easy stuff to work with that you've done before. Do be mindful when we're thinking about log base 10 and what that means, right? That means when we talk about a 1 pH unit change, right? So up here, this is that table from your book. If I go from pH of 2 to pH of 3, some of us might be tempted to say, oh, well, 1 pH unit, that's not that big a deal. Because you're like, oh, well, it's just one number. But if we think about what that means, since we're talking about a log base 10 scale, 1 pH unit is how big a change in concentration? Right, tenfold, right? It is a 10 times concentration change, right? So to say that it is only 1 pH unit is inaccurate. That's not okay, actually. So anyway, pH is the negative log of hydronium or negative log of hydroxide for POH. What that means is we have to know the concentration of hydronium or hydroxide in order to use these equations. A couple of other notes. Don't forget that Kw is equal to hydronium ion times hydroxide ion. That's an important equation to know, right? And a derivation of this is that pH plus POH is going to equal 14, right? And that goes back to if I do a little bit of substitution, this is what I come up with. But either way, these two equations are going to help us to relate all these things together. So let's do a quick pH calculation together. Oh, this is just another figure. This is just lining up two different figures from your book, where let's talk about something that is neutral, for example, right? Which means pH of 7, which means that, again, hydronium is equal to hydroxide at, oh, look, 10 to the negative 7th, right? If we wanted to talk about something having a pH of 1, oh, look, its hydronium ion is 10 to the negative 1, right? Because if we think about that, right, negative log base 10 of 10 to the negative 1 is what? Right, 1, yes? Okay, which means that this must be 10 to the negative 13th because, again, the product of those must be 10 to the negative 14th. Yes? Makes sense? All right, look at this a little bit longer if it doesn't make sense. All right, so let's do some quick calculations. So what is the pH of 0.1 molar nitric acid? All right, so first, let's have a formula, nitric acid. And again, we're going to stay in the land of strong acids and strong bases. So what that means is if I have 0.1 molar nitric acid, I also have 0.1 molar 0.1 molar H plus or 0.1 molar hydronium. Yes? So then, I'm going to set my equation up, which says pH is equal to the negative log of 0.1, and I would do my math, right? And I know that pH is equal to 1. Yes? Oh, and sig figs. There are two decimal places. There are two sig figs, which means that I would use two decimal places. Yes? All right, next up. What is the pH of 0.1 molar sodium hydroxide? So formula NaOH, which is going to do this in solution. So it means if I have 1.1 molar this, I also have 0.1 molar that, right? Now, this is hydroxide ion, not hydronium. So I could do this. And that's going to give me POH is equal to what? Right, 1. And if I know that POH plus pH has to equal 14, then pH is, right, 13, right? Alternative would be that I could set up the equation from the previous page that says 1 times 10 to the negative 14th is equal to 1 times 10 to the negative 1, that's my hydroxide, times my hydronium. And if I do that math, I'm going to find that hydronium ion is what? Right, 1 times 10 to the negative 13th molar. And if I do the negative log of 1 times 10 to the negative 13th, I'm going to get a pH of 13. Yes. So either way I do it, I come up with the same thing, right? So whichever of these equations makes most sense to you, right, that's what you would do. All right. Thank you for listening. Be good. And obviously we will do lots of practice. All right. Be good. See you soon. Bye.